Alright, this video is essentially a little housekeeping that I need to tie up here. I've had some questions about these. I already made a video talking about number 2 here, so I'm not going to go through that one, but I will go over number 1 and 3. And for number 2, I'm not going to write that one up right now, but I will send you to the PDF solutions when I get them. Then I'm also going to talk and wrap up number 1 and 2 on worksheet 2 in a second video here. I might just do it all at once. We'll see. I might not talk my way through this whole thing, I might just kind of see what comes to mind as I'm doing it, and we'll see how it goes. All right. Stone projected at a cliff on Earth, height h, with an initial speed of 42 meters per second, directed 60 degrees above the horizontal. Stone strikes at A. All right, 5.5 seconds after launching, so stone's flying through the air the whole time. Gravity's pulling it down. There's no force propelling it forward. It was given a force when it was first launched, but once it's flying through the air, gravity's the only force acting. So, determine the range of the stone. All right, delta x equals 1/2 at squared plus v naught x t. All right, 60 degrees, that's v naught, not v naught x, that's the angle theta. Time is 5.5. Okay, so that's t. So, x direction, there is no acceleration, right? Ax equals 0. That's part of the deal with projectile motion. V naught x, we have to do a little side calculation, all right? V naught x is going to be v naught times the cos of 60. Cos of 60 is 1/2, so v naught x is half of 42, or 21 meters per second. All right. So delta x equals 21 meters per second times 5.5 seconds. 21 times 5.5 equals about 116. Really 120 to 2 sig figs, but oh well. Whenever I put 120 for an answer like this, people freak out. Like, it's 116. Why'd you put 120? Well, there's only 2 sig figs here, so our answer should really only have 2 sig figs. But it's not too important for physics. We can go with the 3. That's okay. Next one, height of the cliff. H. Well, that's going to be delta y. Delta y equals 1/2 ay t squared plus v naught yt. All right, move this up a little bit. V naught y is v naught times the sine of 60 degrees. So it's 42 times the sine of 60 degrees, which is 36 meters per second. I'll write it like I wrote it up there. All right, so delta y equals 1/2 of negative 9.8 meters per second squared times 5.5 seconds squared. Acceleration in the y direction equals negative g, which is negative 9.8, plus 36 meters per second times 5.5 seconds. So if it didn't have this acceleration, it would just keep moving at that velocity for that amount of time. It would just keep going up. But this portion is going to bring it back down. So let's see what delta y is. 0.5 times negative 9.8 times 5.5 squared plus 36 times 5.5. It's about 50 meters. Delta y. Delta y equals 50 meters. Therefore, Therefore, h equals 50 meters. Delta y is technically positive 50 meters. Went up 50 meters to get to there. So that means the height of the cliff is 50 meters. Determine the maximum height of the object. Well, the key here is at max y, vy equals 0. So basically, that's what we're going to do here. So when you throw something up in the air at its peak, its y velocity is 0. Its x velocity is still 21 meters per second. Still moving forward. So what do we do with that? Well, we're looking for h, which is delta y, to get to the peak. Well, the time to the peak, often if it was symmetric, you could just say the time to the peak is half the total time of flight, but it's not symmetric. That's kind of the point with this one. So you can't say it's half of it. So what do we do? Well, timeless equation. V squared equals V naught squared plus 2a delta y. I will put y subscripts on these variables just to be neat there. Remember, we're solving for delta y. So Vy is the final velocity. So the velocity at the peak, well, that's going to be 0. The initial y velocity is 36 meters per second. That's going to be squared, plus 2 times negative 9.8 meters per second squared times delta y. All right. So we're going to take this one, bring it over here to make it positive, right? So it ends up being about 2 times 9.8. Well, I'll just do it like that. I bring this over to this side, so that makes it 2 times 9.8 times. Now I'm going to ditch the units in here. I already wrote them down once, so really, 30 equals 36 squared. So delta y, bring this up over here, delta y equals 36 squared over 2 times 9.8. I usually like to solve stuff for variables first. Should maybe start modeling that for you guys so you can get used to that. That's a skill you should have in AP Physics C, is not worrying about numbers so much and solving stuff in terms of variables. Alright, I have a classic story about that. I probably have told you it before, but I'll tell you it again sometime, about being in a freshman physics class at RIT, and the professor freaking out because of somebody having stuff in their graphing calculator and totally eliminating calculators for the rest of the course, and everything was done in terms of variables. Anyhow, delta y for this ends up being about positive 66 meters, which means h equals 66 meters. So technically delta y is positive to get up to the top. Therefore, the height is a magnitude. Height's always a magnitude, is 66 meters. All right. Number 2 here, I got to write it up anyway, so probably not going to talk about it, but I'll talk about it again. I'm not going to solve it in terms of the numbers. Delta x equals v naught x times t. Delta y equals 1/2 ay t squared plus v naught yt. I didn't even write down the acceleration. Delta x equals v naught cos theta times t. Delta y equals negative 1/2 gt squared plus v naught sine theta times t. I'll solve this. This is a case where, I've done this problem now 3, 4, 5 times in the last week. So it's, don't have to think about it too much. I know how to do it. That's what you should do to study, right? If you got a problem that you've seen the solution to, you're not really sure how to do it, mimic it. Mimic that solution. Work through that solution. Write it out, okay? Then try to go back and do the problem again, kind of from memory of the solution. And then, if you can't, look at the solution, pick up where you left off, and it becomes an iterative process where when you fail, when you don't make it through the whole problem, you have to go back to the beginning and start again. Kind of like learning a musical piece, right? Until you can play the whole thing through, you don't really know it. So, anyhow, I'll just continue on here. I got to solve this one for t. This is the way I did it in class. Delta x equals v naught cos theta. I'm going to plug it in over here for t in a second. Delta y in this case, I probably should have made a drawing here, right? Delta y equals 0 because it starts here, ends over here. Delta x is the range, we call that. So this is 0. So we bring this over here, 1/2 gt squared equals v naught sine theta times t. T's cancel. One of the t's cancels, I should say. So I have now this going in here for this t. So 1/2 g times delta x over v naught cos theta. I just kind of plug these in kind of raw to start off with. I don't try to be too fancy. I am going to rearrange this to look a little bit better before I start moving stuff around. So I write it as g delta x over 2 v naught cos theta. Just makes it look a little nicer. It's kind of the way we do it in physics, v naught sine theta. And now I am going to bring this up over here. So g delta x equals, and again, this is the second time I've recorded this one even, so, you know. Alright, so I'm going to just write this a little bit differently. G delta x equals, oops, it's v naught squared. V naught squared times, I'm going to put it in parentheses because it's a trig identity. This double angle formula, right? So this whole thing equals sine of 2 theta. Alright, so I'm kind of running out of room. I'll bring it up over here. So I have g delta x over v naught squared equals sine of twice the angle. Now from there, to solve for theta, I do have to start plugging stuff in, right? So take the sine inverse of both sides. I'm going to put in numbers now. So 9.8 times 1,000 divided by 300 squared equals twice theta. Divide both sides by 2. Theta equals, and then I forget now. I should have just type it in quick here. Alright, so sine inverse of 9.8 times 1,000 times divided by 300 squared divided by 2, about 3.1 degrees. That sounds familiar. Alright, hovercraft, so there's one I'll talk through a little more. Hovercraft moving forward at 10 meters per second, accelerates, speeding up at a rate of 2 meters per second for 5 seconds until it reaches its max speed. Alright, cross beam pushes on the hovercraft perpendicular to its motion, shifting it sideways as it moves with an acceleration of 0.3 meters per second. How far off track will the hovercraft be after 20 seconds of motion if no corrections are made? Alright, so it's already moving, right? And it speeds up for 5 seconds. Oh, it should be getting a little bit bigger. 1, 2, 3, 4. Oh, alright. And something starts pushing on it, alright? So sideways with that acceleration. I guess I should have started it down here. So I guess I'm gonna draw it moving this way. So what happens is it's still speeding up, but something's blowing it off track, right? So it's still got this component that's getting longer, right? But it's also now starts to accelerate this way as well. Now this acceleration isn't that big. I kind of got a little bit drastic there. So anyway, how far is it blown off track? Well, if it never had that cross breeze, it would start going in a straight line. It would be going in a straight line, right? But it got blown kind of in a curved path. So how far off track is going to be this distance here? That's the deflection, right? How far is it deflected? So it's this distance, this delta y, that it happens while it's blowing this way. Turns out for this one, the delta x stuff doesn't even matter, right? Oh, it says until it reaches its max speed, so I guess it's moving at constant velocity in the x direction. So maybe I drew that a little wrong. Doesn't really matter though, because delta y is going to be independent of the forward motion. So delta y is how far off track. So delta y equals 1/2 ay t squared plus v naught yt. Well, v naught yt is simply 0. So delta y equals 1/2 ay, which is 0.30 meters per second. Now the way I drew it, I should probably make this negative, but it doesn't really matter. 20 seconds squared. So it's going to be blown off course for 20 seconds. 0.5 times 0.3 times 20 squared equals 60 meters. And it's always kind of interesting to see, okay, so wait a minute, how far forward did it move in that same time? All right, so delta x is going to be, well, you kind of have to break it into two parts, right? 10 meters per second, 2 meters per second for 5 seconds. So it's actually moving forward at 20 meters per second when it, you know, starts getting blown off course. And actually, these should not have gotten longer. There's no x acceleration after that point. So the x displacement here would be simply the v naught x times t, which would be the 20 meters per second that it got up to by the time that cross breeze started, times 20 seconds. So, 400 meters it moved forward, and it deflected off 60 meters, right? So anyway, this is the answer here, delta y. All right, I'm going to pause this now and start another video finishing up this worksheet.